Okay, let's start class. So last time we talked about the baseline uh, category logit model and the cumulative logit models. So I think we stopped at slide 16. So we will just continue. So last time we finished by this political ideology and party affiliation example. So we can also do the inference about the cumulative logit model. Remember the difference between the baseline category logit model and the cumulative logit model? The difference is that depends on the response variable is nominal or ordinal. If it's nominal, that means for the response, we have multiple category, but there's no order. So there's no ordering structure, so we just use the baseline. So we set the last one as the baseline group, let's say, then all the others group compare with the baseline group. And each pair, we fit a logistic regression model, right? And then we can estimate the probabilities just like we did in the logistic regression, and we can interpret the results, okay? So if we have the ordinal response, then we can use the cumulative logit model. Especially last time we talked about the proportional odds. So the proportional odds for the cumulative logit model, assuming that for the different categories for the y's, the cumulative logit has the same shape. Okay, so we can just shift it, the curve, either to the left or to the right, so that all these different categories for the cumulative logit model will have the same exactly curve. So they will have the same shape. So in other words, for different J is the category index for the response. The logit for the cumulative logit model, so which is the logit for the probability of y is less than or equals to j. So this model is the alpha I, or I'm sorry, alpha j plus the beta x. So you can see the only one that changes with the j is the intercept, but the beta is the same. In other words, the effect of the x on different levels of j for the cumulative logit model is the same. Okay, so that's the assumption, and we will talk about how to relax this assumption in a minute. Okay, and for the cumulative logit model with proportional odds, we can also do the inference just like before. So for this, for the political party affiliation example, so remember we have 5 categories for the political ideology, right? So we have from the lowest, that's the most liberal, to the slightly liberal, moderate, and for this one is slightly conservative and very conservative, right? So we have two predictors. One is the gender, and the other one is the party affiliation, right? So we want to test, let's say, if the party affiliation has a significant effect on the political ideology, on the response. So what we can do is we fit another model, fit 2. That is to model the ordinal response using only the gender, not using the party affiliation, right? Then we have a deviance. Okay, so what we do is now we can do the comparisons between the fit 1 and fit 2. Fit 1 is the one that includes gender as well as the party affiliations. Okay, and so the fit 2 is only with the gender, and you can see the degrees of freedom is 1 because the number of parameters differed by only adding the party affiliation or not. So there's only one difference in the number of parameters between these two models. And the test statistics is this one. That's the difference of the deviance. And the p-value is highly significant. So that means what? That means the party affiliation has a significant impact on the political ideology, right? And this can give you the 95% confidence intervals using the likelihood ratio approach. Okay, so you can see for the party affiliation, it is significant. Why? Because you can see the lower limit and upper limit for the 95%, they exclude the 0, right? And you can see the lower and upper limits are far from 0. So that's why the party affiliation has a very strong impact, right? But for the gender, you can see the lower and upper limit actually includes 0. So that means the gender does not play a significant role for the party affiliation or for the political ideologies. Okay, so that's how we do the inference. We can do the test, likelihood ratio test, and also we can have the confidence interval. Okay, so the cumulative Logit models which utilize the ordinality of y usually have a simpler model, and we've already talked about that, right? Because of the proportional odds, so we will have fewer parameters because the beta is irrelevant to the j, right? So we'll have fewer parameters. That means the power will be higher, okay? And the power advantage over the baseline category Logit model, okay? So let's see this example. So this is the happiness and family income example, okay? So the response is happiness, okay? And the predictors is the family incomes, okay? For the response, we have 3 levels, okay? So we have the lowest level is not too happy, and the middle one is pretty happy, and the highest one is very happy. So we have 1, 2, 3 levels for the Y. So you can see there is some order. So we can treat the Y as an ordinal response. Is that right? But also we can ignore the ordering information. We can just treat it as a nominal response. Okay, let's see what is the difference between these two models. Okay, so the family income also 3 groups: below the average, average, above the average. Okay, so we can fit. This is the one that treat the Y as the ordinal. So that's the proportional odds Logit model. a cumulative logit model, right? So we can, so this is the data, okay? So we fit the proportional odds cumulative logit models. Don't forget, we have a parallel is true. That's for the proportional odds. So that means all these curves are parallel, right? Parallel means if I shifted this one to here, they perfectly match. And same thing here, okay? So that's the parallel means. So we have these models, okay? And we also have this one. So this one is without income. So just fit an intercept only model. And we can do the test, likelihood ratio test. So you can see the p-value is marginally significant. So what we can say is, so the family income is kind of related to the happiness, but that association is marginally significant. Okay? So, and we can also treat both variables as nominal here. Okay, so we can treat the income as nominal, and we can also treat the happiness as nominal. So in that case, we cannot use the cumulative logit anymore, because if you treat it as nominal for the response, then you have to use uh, you, you you cannot use the cumulative logit. So we can use the baseline category logit models. Okay, so uh, we can so the model becomes this. So you can see how many parameters do we need. We have 3 categories for the response, right? Not too happy, happy, pretty happy, and very happy, right? So we have 2 models, okay? And the baseline model is what? Is very happy, right? So the first one, if J is 1, that means not too happy over very happy, the log odds ratio. Okay, so that's the logit between the first and if J is 2, that means it's logit for uh, pretty happy and very happy. Okay, so we have these 2 models, right? So how many parameters do we have? For each model, we have 3, right? So in total, we have what? We have 2 models. So in total, we have 6 parameters. That's for the baseline category logit model. Is that right? But what about the proportional odds model? So for the proportional odds model, we have we we only have let's see here we have the 2 alphas, right? 2 alphas, but with only and for the betas we only have 1 beta because we treat it as ordinal, right? So we have 2 alpha, so we have 3 prime. Okay, so you can see there is a yeah. So you can see using the proportional odds can save 3 degrees of freedom, right? So the model is simple. Okay, but here let's say we do it as a baseline logit, baseline category logit model. Okay, so here if we treat as a baseline category logit model, and we want to see if the income is significant or not. Okay, so we will fit a model. So here, the fit 3 is the baseline category logit model, right? So you can see the income now becomes a factor. Factor means it's nominal. Okay, so we have that's the baseline category logit model. And this is still the baseline category logit model. But this time we don't include the income. We just have the what? The intercept. Okay, so if we want to test the income is significant or not, what is the degree of freedom? Now, here we are not comparing with this one. No, because this is we are comparing the baseline category logit model with the proportional odds cumulative logit model. Okay, so here we are only focusing on the baseline category logit model, but we are testing if the income is significant or not. Okay, so it's different. So the degree of freedom is 4. Why? Because now we don't have income. So how many parameters do we have for the income? Don't forget we have 2 sets. We have 2 equations, right? So for one equation, we have 2 betas. So for 2 equations, we have 4 betas. So the difference of the parameter here is what? Is 4. Okay, so that's why when we compare these 2 models to test if the income is significant or not, you can see the degree of freedom for the test is 4. Is that clear? And the test statistic is 4.12. And you can see the p-value is not significant. Okay, so if you go back to here, you can see the p-value for the income is marginally significant for the proportional odds cumulative logit model. But p-value becomes not significant. Why? This test does not assuming as much about the model structure. For example, the linearity for the income effect. And it treated both variables as nominal, so that gives more degrees of freedom for the test. That means lower power. So more parameters. So if the model becomes more complicated, like here we have 4 extra degrees of freedom used to model the income. Because of these 4, that makes the power is low. So the p-value is not significant. Is that clear? So let's say here, let me stop this. I think maybe let me show you where's the table. Statistics table. Where's the table? Let me see. I cannot. Let's see. Where's the table here? Okay. So let me share again. So you can see the table, right? So here, for this one, let's say the test statistic is 4.1, right? With 4 degrees of freedom. Okay, but if we look at the chi-square table, okay, so 4 degrees of freedom. If you go to the 4 degrees of freedom, that line, and what we have is between these. So you can see the p-value is not significant, right? But if we use the proportional odds cumulative logit model, let's just say, for example, if the test is still 4, but now the degree of freedom is 1 because we treated the x as numeric, right? And also we treated the response as ordinal, right? So in that way, we only use 1 extra parameter for modeling the income. So the degree of freedom is 1. So if it's 4 for the 1 degree of freedom, let's see, what is the p-value? You can see the p-value becomes significant because that's between these. And you look at the p-value, it's less than 0.05. So you can see by adding more parameters, the power is low. That means it's more difficult to reject the null hypothesis. But if the number of parameters is fewer, then we can easily, it's much easier to get the significant results. You see my point? So that is the point that I made. So if we have more parameters, of course, the test will be much more difficult to get significant results. Okay? Okay, now this is to interpret the Logit cumulative link model with the interpreted by the latent variable model. Okay, so now you can see, first of all, what is cumulative link model? Now it's changed. Why it's link? Because don't forget, here, for the cumulative Logit model, okay, if you go to, let's see, where is it? Yeah. We use the Logit equals to that. But Logit is just a link that we use. Do we have to use Logit for this one? No. We can change Logit to what? To, like, for example, we can change it to probit. Can we do that? Yes. We can also do that. Or using the identity link. So cumulative model, that's very general. We can have cumulative link model. That means we don't have to be using the Logit link. We can use other link, for example, the probit link. Okay, so that's why here we call it cumulative link model. That's just for general purpose. Okay, so where is it? Yeah, so this includes the cumulative Logit model as one special case that use the Logit link. Okay, but that also applies to the cumulative probit models as another special case. Okay, so that's what. So for all these cumulative link models, we can interpret through the latent variable linear model. So that's what the slides called meant. So here the proportional odds structure is implied by a simple latent variable model with observed response as a crude measurements of a continuous latent variable. Okay, so here for the cumulative link model, you should first, you know that for this model, the y is what? Y has to be ordinal. That's, you have to know that. That's ordinal. That means the y has the ordered categories. Okay, so that's what we observed. But if we interpret through the latent variable model, so that means there's an unobserved continuous latent variable called y star. That actually is not observed, but that's the underlying number that really plays in effect. Okay, so here, instead of model the response y, that what we observed, we can, how about we model the y star? Then you may ask, what's the relationship between y star and y, right? So the y star, this is observed, but this is unobserved, right? So the relationship is that now the y star is truncated in, it is actually in, we can cut the y star into different regions. And then let's say we cut it at alpha 1 through alpha c. Okay, so if the y star is between the alpha 0, that means it's the minimum y star it can reach. Okay, we can treat it y alpha 0 as negative infinite. Okay, anyway, this is the minimum we can have for the y star. If the y star is between alpha 0 and alpha 1, then what we observed is not y star, is what? Y equals to category what? 1. Is that clear? If it's between alpha 1 and alpha 2, then we didn't observe y star, but we observe y equals to what? 2, and so on. Okay, so that's up to class category C. So that's the underlying latent variable, which is continuous but not observed. What we observed is just the crude measurements of y star. Okay, then the cumulative link model is to model the y star as a linear function of the predictors that we have. Okay, then you may ask, then what is the model using that for the latent, that use the latent variables as the response, and the model that is the cumulative link model that we talked about before? What's the relationship between these two models, right? Are they exactly the same, or they are not the same but they are related? Okay, and I tell you they are not exactly the same, but they are very similar. Okay, so if we model through the latent variable, just as I said, then the latent variable model, let's say, is this one. Okay, remember, this is the latent variable model. That's the y star. That clear? But what is the Logit cumulative link model? Okay, cumulative link model is this one. Is that clear? So the latent variable linear model is this one. Make sure you know this, okay? So this is this one is this one, okay? So are they the same? No, you can see they are not the same. But what about, is there any relationship? Yes. And here is the tricky part. The tricky part is for the ordinary, for the latent variable linear models, look at the betas for the x. The beta for the x is what? Beta 1. But what about the coefficient for the x1 here? It's negative beta 1. You see that? For the beta 2, here in the latent variable model, it's beta 2, but for the cumulative logit, it's negative beta 1. It's negative beta 2, and so on. So you have to be careful. So these two models are not exactly the same. They differed by two things. One is the coefficient, they flip the sign. Beta 1 for x1 in the latent variable, then it becomes negative beta 1 for the cumulative link model. Is that clear? And another difference is for the latent variable linear models, we don't have the intercept. There's no intercept. But here we do have some intercept. Okay, so these are the two differences. But they are very close, right? So when we interpret, you have to be very careful, okay? So depends on what it showed. So you need to, so if the model shows you the latent variable linear model, then if you interpret it using the cumulative link model, then make sure you know that the beta is actually negative in the cumulative link model. Okay, so that's the relationship. And some of you may curious about why there's such a sign flip. Okay, so here, look, here, the x, 1 unit increase in the x. So the y star will increase by what? Beta 1 units expected. Is that right? So when the x1 increases, okay, so the y star will increase by what? By beta 1. Is that right? But here, what we modeled, we actually modeled the length for the cumulative part, but that is towards what? Not towards y goes larger, but towards y is smaller. So that's the left side of the y. Is that clear? So that is the link for the probability of y is what? Less than or equals j. So that's the difference. Because this is towards the y is smaller, becomes smaller. But this is go with the y star is goes higher. So that's why if x1 increases, the beta star will increase by beta 1 unit. So if the x star increases, so the probability of having the y is less than j is what? Is decreasing. You see that? So that is the reason why we have a negative beta here. So the sign is different. In other words, if we change in a different way, if let's say we have the link for what? For the p is y is greater than or equals to j, then we will have the same sign. Okay, but here we are modeling in the less than or equal to. So that's the reason why we have a negative beta 1 here, but a positive beta 1 here. Okay, so that's the explanation why we have a sign difference. Okay, so now let's back to the why it's called cumulative link. Okay, so if the link we use is probit link, remember the probit model? Okay, probit model is to model the z-score using a linear function. Remember, right? So that's if we use the probit, then the latent variable linear model, this one, will have the epsilon, that's the random part, that's the random error, will follows a what? Follows a normal distribution. And that's a special normal distribution called a standard normal distribution. That's the mean is 0 and the variance is 1. Is that clear? But if we use the Logit link, so that's the cumulative Logit model, then the epsilon is not following the standard normal distribution, but following a what? The epsilon is follows a standard logistic distribution. So there is a probability distribution called the logistic distribution. And the standard logistic distribution is the epsilon that follows. And that corresponds to the cumulative Logit model. Okay? And we can have some other link function. So different link function we can always model by that. But the only difference between among these different links is just the corresponding error distribution are different. Is that clear? So that's a very general framework that we can interpret the cumulative link model through the latent variable link linear models. Okay, so that's the interpretation. Okay, so after we talk about that, we can also check the ordinal model goodness of fit. And we can check the ordinal model goodness of fit. So that is when the response is ordinal, and we can check overall that model fits the data well or not, right? That's the essence of, that's the purpose of doing the goodness of fit test, to see if the model fits the data well or not. Okay, so we can do it through the chi-square test using the residual deviance. Okay, so for the political ideology example, so we fit the proportional odds cumulative Logit model using the party and the party affiliation and the gender information. And after we did the fit, you can see the residual deviance is what? Is 9.8 with 10 degrees of freedom. So the goodness of fit test is just using the test statistic is 9.8 and the degrees of freedom is 10. We can find out the p-value. Okay, so we can do it using 1 minus that. So why is 1 minus that? Because this one only gives you the chi-square, gives you the, let's say the chi-square distribution looks like that. Let me just erase that. So the chi-square is actually a little bit skewed. So let's say this is the chi-square with degrees of freedom is 10. Okay, so let's say this is 9.81. Okay, so if you use the p chi-square 9.1 degrees of freedom is 10, it gives you the area on the left side. Okay, so 1 minus that gives you the area on this side. And that is the p-value. So that's why I use 1 minus. Okay, and if you go to the table for the chi-square, look, this is the probability of what? A larger p-value or chi-square value. So that is larger means that's the left side or that's the right side. I'm sorry. Okay, so that gives the p-value. So you can directly get that from the table. But if you use the R to get that, okay, then you need to just do the 1 minus. Okay, so that's the p-value. Okay, so that's the goodness of fit. As I said, goodness of fit just tell you the overall, the model fits the data well or not. Okay, it's not doing the model comparison. Just tell you the model fits data okay or not. Okay, so for the cumulative Logit model, we talk about, so far we only assume the proportional odds assumption, right? What is the proportional odds assumption? Proportional odds assumption is that this. So that means the effect of X on the log odds of response in category J or below, that is the same for different levels of J. So that means these curves have the same shape. But we don't have to assume that, right? That's a very strong assumption in practice. So we can relax it, okay? So here is just saying we can model it through the cumulative Logit, but without assuming the proportional odds assumption. That's fine, okay? And so for the political ideology example, so we can fit a cumulative Logit model without the proportional odds. So how to do that? You see, that's the fit 2 is the one that without proportional odds. That is without the parallel equals to true option. So you look at this line, okay? So the main difference is in the family statement. Family is cumulative, that's it. Stop there, okay? But for the proportional odds cumulative Logit model, we have the parallel equals true. So that's the, you see that? Parallel equals true. So that's the difference. If you don't specify that, that means we model the cumulative Logit without proportional odds. Okay, so then we can compare if the proportional odds assumption is reasonable or not. Right? We can compare these two models to see if these two models with and without proportional odds are significantly different. If there's no significant difference, then we say assuming the proportional odds is good. Why? Because the model is simple, plus there's no significant difference between these two models. Okay, so the fit is the one that's with proportional odds. Fit 2 is the one that without proportional odds. You can see we do the test, the degree of freedom is 6, and the test study is this one, 6.2. And you can see the p-value is not significant. Okay, so here, why is 6, you may ask? Because compare these two models, the 6 is the difference, is the number of additional parameters that we used in the without proportional odds model. Is that right? So how many additional parameters do we need? We need 3 more parameters from the party and 3 more parameters from the gender. Is that right? Let me explain more detail. Maybe some of you are still not clear. So why it's 3? So here in the political ideology data, how many categories for the response? The Y has how many levels? Y has 5 levels. Is that right? So 5 levels from very liberal to very conservative. 5 levels. So that means how many cumulative Logit model we have? So how many Logit model do we have? We have 4 models. Is that right? So the first one is to model the Y is less than or equals to 1, the lowest level. Then it's 2, then it's 3, then it's 4. Why not 5? Because 5 is 1, is a constant, so we don't have 5, right? So we have 4 models. So for the proportion with the proportional odds model, we have 4 intercept, right? 1 for each model, right? But we have 1 parameter for the party and 1 parameter for the gender. Is that right? So that's the proportional odds. Without proportional odds, so we still have intercept 1 for each model. So that part is the same between the with and without proportional odds. But for the party, how many parameters do we need? We need 4. Is that right? 1 for each model. Is that right? So we need 4 betas for the parties and 4 betas for the 4 coefficients for the gender. Is that right? So you can see what's the difference of the number of parameters do we need. So you can see without assuming the proportional odds, we have 3 additional betas for the party and 3 additional betas for the gender. Is that right? So that's why we have 3 from party, 3 from gender. So that's why the difference is 6. Okay, so you can see the p-value is not significant. So for example, if I leave this blank here in the midterm 2, I assume you should be able to find out this is 6. Okay, so that's why those parts that I explained a lot, these are the things that you should know. So why it's 6? Because we have 3 from party, 3 from gender, right? So the p-value is not significant. So that means what? So that means there's no significant difference between with and without assuming the proportional odd model. Then we should just assume with. assuming the proportion R is good enough. Okay, so that's the how to check if we should assume proportional odds or not. Okay, so I think we've already explained that. Oh, yeah. So we can also interpret through the probabilities. So we can interpret the cumulative logit model through the odds and odds ratios and a different way. And if we interpret through the odds and odds ratios, then we have to, that is based on exponential of beta. Okay, for 1 unit increase in the x, and while fixing other x variables, adjusting other predictors, then the odds ratio, right? So the odds will increase by exponential beta. Odds will increase by exponential beta, right? And the odds ratio is the exponential beta for 1 unit increase in x, adjusting others. Okay, so that's how we interpret. And a simpler and more direct way for the interpretation is just not using the odds and odds ratio, but just using the probability. We can still do that. Okay, so if the x is quantitative, then we can just compare the extreme category probabilities on y. That means the highest and lowest levels of y at the maximum and the minimum values of x. So that's one way. If the predictor is categorical, then we can compare the extreme category probabilities. That means the highest and lowest level of y for different groups of x. Okay, and this is controlling other variables. Okay, and we can also interpret through the average marginal effects that we talk about in the logistic regression. Okay, so here is an example. So that's the mental impairment example, and I will illustrate these points through these examples. So here, this study, the Y is the mental impairment. It's ordinal with 4 categories. 1 is well, 2 mild, 3 moderate, and 4 is impaired. Okay, and we have 2x. X1 is life event index. So this is the numeric composite measure of number and severity of the important life events, such as like the birth of children, birth of child, new job, divorce, and like that. So the larger the X1, that means the harder the life and more uh, life events and the severity of the important life events. Okay, and for the X2 is the social economic status, SES. So the 0 means low and the 1 means high. Okay, so this is the, so we can use the latent variable induced form for the cumulative logit model with proportional odds. We can use this model. Okay, so to model the cumulative logit proportional odds model, we can do it in 2 ways. One way is through the one that use the VGAM library. Okay, we can do it like that. And this is the model that gives you the coefficients and the summaries for which model? For this model, for the cumulative logit model. Is that clear? So for the VGAN library gives you this model. It's the cumulative logit or the cumulative link model with proportional or without proportional odds is this one. Okay, and we can also model it in different way. We can model using this latent variable linear model. Is that clear? So to model in this way, we can use a different package called mass. We've already used this library before, right? So in this library, there's a function called the POLR. So POLR is a function that to model the cumulative logit or the probit models, but through the latent variable models. So this can do the same job, except it outputs the model which is this model. Is that clear? So that's the difference between the POLR function and the function in the vegan library. Okay, so that's the difference. Okay, so for the POLR, the response has to be a factor. So that's why I put a factor here. So we have the life and SES as the predictors. And you can see this is the model, shows the coefficient. And you can see it does not have an intercept. Why? Because this model, for the latent variable, it does not have an intercept. Okay, as I said, there are differences between these two models. So the sign is different for the beta, right? And the second is the for the this one we have an intercept. For this one we don't. And actually, there's another difference. For the latent variable model, we have a what? We have an error term. But here we don't have error term. We just model the probability directly. Okay, so that's the difference. So now let's see. So the model shows this is the results. Okay, so here the life has the coefficient is 0.318. Okay, and SES is negative 1.1. So what does that mean? So SES is negative 1.1. So that means the mental impairment tends to decrease with higher values of SES. Is that right? So when the SES increase, the mental impairment actually decrease. Okay, so mental impairment decrease means feel so that means it's well. Okay, it starts from the well, mild, and so the SES increase means from low social economic status to high social economic status. So that makes the Y reduced. And that makes sense, right? And similarly for the life. So the life has a positive. So that means if we have larger value of that's the life events, then the mental impairment tends to increase. And that also makes sense because X1 is life events index. If that increases, that means that that subject has faced more important life events and more severe important life events. Of course, that the mental impairment will increase, right? And that you have to interpret through the latent variable model. Okay, so we can also do the prediction for the probabilities. So you can see the first one, I do the prediction at SES is 0 and 1 for the life is at the mean for the life event index. That's the average. But SES is low and high. Okay, so low and high. So compare with the low and highs, you can see the probability of having the Y is 1. That means it's well, it's much higher when the socio-economic status is high. But this one is much lower. Okay, so you can see the effects. Okay, but here, this is showing the SES is 0. So that means the socioeconomic status is low. But we compare the minimum and the maximum. So the range function in the R, it gives two numbers. The first one is the minimum level. The second one is the maximum. Okay, so in other words, this one, the first row here is showing the probability for the subject that has the well for the mental impairment with the SES is 0. That means it's the low socioeconomic status, but the number of major life events index is the minimum. That means that that person has not much major life events. So that's why this one is high. But this one is maximum. That although with the same socioeconomic status, but this person faced lots of challenge in the life, so that's why the chance to have the well is much lower. Okay, but this one, the last two, these are for the SES is high. Still comparing the minimum and the maximum for the life event index. You can see compared to these, when we have a higher socioeconomic status, the chance of being well is much higher. Okay, so that's how we can interpret the results through the probability directly. Okay. Any questions so far? Okay, so and this is to this slides is showing you the example to interpret through the average marginal effects. Okay, so it's self-explained, but there's a typo here. So it's 0.198. It should be 0.199. And 0.171, it should be 0.166. 166. Yeah. Okay, so these are, but it's close. Okay, so you can take a look. So this is to interpret through the average marginal effects. Okay. Okay, so the next one is a different cumulative link model. That's the cumulative probit model, as I said. Now this time, the link function is the probit link. Okay, as I said, for the probit link, the latent variable model epsilon follows a standard normal distribution, while for the for the cumulative logit model, that follows a logistic distribution. Okay, so that's the difference. So now let's still using the political party examples. So we using the POLR again, but this time the method is probit. Okay, and as I said, this one gives what? These coefficients, these, oh, what? Okay, these, uh, yeah, okay, these coefficients are for the latent variable model. Okay, so if you want to, if I ask you, so what is the coefficient for the cumulative probit model, not the latent variable model, for the party, then it will be what? It will be negative 2.03 for the party and positive 0.007. That's for the gender. Is that clear? So there is a sign difference. Okay, but these coefficients are for the latent, okay, latent variable model. And these are for the cumulative probit model. So different. Okay, these are the different. The difference is in the sign. Okay, and you can see for the party we have the coefficient is 2.03. So that means what? That means that for the normal latent variable model, why it's normal? Because the epsilon follows a standard normal distribution. Okay, so that's why it's called it's normal latent variable model with higher values of y star represent the greater conservative and epsilon follows normal 0, 1. And the estimated mean political ideology for the Republican is 2.03 higher than the estimated mean for the Democrats. So this is 2.03. That is comparing with the Democrats. So for the Republicans, it will have be 2.03 higher than the Democrats for the Y star. And remember the Y star, that's the unobserved continuous. Okay? So the larger the Y star, that means it's what? The more conservative. Is that right? Conservative. Why? Because here what we observed Y is starting with the one is most liberal, right? To 5 is the most conservative. So Y star is increases, that means more conservative. Okay? So that's the interpretations through the latent variable model. Okay? Using the POLR. Okay? And the good things for using the latent variable model is that since the latent variable model is regression model, is that right? Because the Y star is now the Y star is numeric, is continuous. So we can interpret the models and summarize the models through what? Through the tools, statistics that we can use, that we can borrow from the regression model. Okay, one of the popular statistic that we use for the regression model to summarize the model performance is what? Is R square. Is that right? So we can also use R squared concepts for the latent variable model here. Okay, and for the if you use the probit model, the error follows a standard normal, so the variance is 1.0. If you use the cumulative logit model, then the error distribution is the standard logistic model, which the variance is 3.29. Okay, so we can fit the latent variable model using the POLR, and then we can find out this is the R square from the logistic latent variable model. Okay, and this is the R square from the normal latent variable model for the cumulative probit model. And look how we calculated how I calculate the R square. I use the variance for the linear predictors over the variance for the linear predictor plus the error. That's the R square. Okay, so that's how we define R square, right? So we can define what is R square. R square is sum of squares for the fitted values, and the sum of squares for the fitted values plus the sum of squares for the errors, right? Or we can write it in different ways. If you are not feel comfortable looking, it's the same as 1 minus the SSE, that's sum of squares error, divided by what is the sum in the denominator. That's the SS total. Is that right? Sum of squares for the total. So maybe most of the textbooks use this formula, 1 minus the SSE over SS total. But what is SS total? That's the SS for the fitted plus the SS for the error. And the 1 minus that, also you can use the SS fit over that, right? So here, that's the variance for the linear predictor over the variance for the linear predictor plus the error. How do we get the error? Remember, if it's logistic, then the error follows a standard logistic regression, standard logistic distribution. The error is 3.29. So that's why I put it here. For the probit model, then the error follows a standard normal. So the error is 1 for the variance. Okay, so that's how we find out the R square. But in both approach, you can see the R square is about 50%. So that means by using the gender and the party affiliation information, the model can count about half of the variation for the Y star. Y star is the unobserved latent variable for the party for the political ideology, which is continuous, and the higher the Y star, the more conservative it is. Okay, so that's the interpretations for the models through the R squares. And the last 4 slides, 1, 2, 3, 4. These are just giving you some alternative models for modeling the nominal multi-category response. In other words, these are giving you the alternatives for the baseline category logit models. Is that clear? So if the response is not ordered, it's not ordinal, but it's nominal, okay? So baseline category logit model is not the only choice. Now that is one of the choice that you can use. And we can use some others. So what are the others? One of them is called adjacent category logit. And that idea is very intuitive, because for the baseline category logit model, why we have to compare with a baseline group, right? Why not comparing with other groups, not the baseline group? I don't have a baseline group. I want to compare with others. That's fine. So one of the approach is called adjacent category logits. So instead of comparing with a baseline group, it compare with its adjacent group. Okay. For example, we have C categories. Okay. So we can, let's just index the category 1, category 2 to the category C. Okay. So that's the index. So we can model the log for the pi j over pi j plus 1 using this. Okay. In other words, the first model is to model the log of the ratio for the probabilities for the category 1 and category 2. Then the second model is model the log of probability for the category 2 over category 3 and so on. So that's one way to do that. Okay, so that's the adjacent category models. And we can, as an example, let's see, we can use these adjacent category logit model for the political ideology example. So this time, I use the VGAM, use the VGLM, but this time the family is ACAT. The first A is adjacent. CAT, that's category. So ACAT, that means we are not using the baseline, cumulative, no. We are doing the adjacent category. And the parallel is true. That means what? The parallel is true means that we assume the proportional odds. Okay, and reverse is true. So that keeps some, that means it's j over j plus 1. And you can do it in the other ways, like j plus 1 over j. That's fine. That's a different. Okay, so just specify the directions that we used for the adjacent categories. And this is the summary results. Okay, so you can see now the party has the coefficient is this one, and the gender is this. Okay, and I have the interpretations here. And it's very self-explained. You can take a look. Okay, after class. And the next one is the sequential logit model. Okay, so for the sequential logit model, it's a different. So slightly different. It's modeling the log of what? The pi 1 over what? Over the rest of the categories, cumulative probability. And the second one is pi 2. That's the second category's probability over what? Pi 3 plus 2 to the pi c. You see that? And what about the last one? The last one is pi c minus 1 over pi c. So that's called the sequential logits. Okay, so that also called the continuation ratio logits. Okay, so the sequential logit model form is useful when we have a sequential mechanism, such as like the survival through various age group. And that can determines the response outcome. So sometimes this one is easy for interpretation purpose. So that's the reason why people proposed different models, like the baseline is one, adjacent category is one, and the sequential logit is one. These are just for different purpose. Sometimes for this data set, for this research, sequential is the most interpretable one. It's the one that makes most sense. So that's why we use that. Okay, so that's how we choose which one we should use. So let's see an example. So this is a study that cross-classified a sample of children by its tonsil size and whether they were the carrier of a certain bacteria. Okay, so the tonsil size is the response, has three ordered outcomes: not enlarged, enlarged, and greatly enlarged. Okay, and the counts in those categories are 19, 29, 24 for the carriers, and these for the non-carriers. So the sequential logits that we used here is very natural. Why? Because the sequential process by which a subject can develop greatly enlarged tonsils. So the tonsil starts in the not enlarged states and may becomes enlarged. So that's the way that's probably best explains the results. Okay, so here the first model is this one. So the pi 1 is the probability of not enlarged, over enlarged, right? Pi 2 is enlarged, pi 3 is greatly enlarged. But we can say both pi 2 and pi 3, that gives the probability for enlarged, right? And for this one is enlarged against greatly. So in that way, we have a better interpretation. Okay, so, and this one, we can still use the proportional odds assumption. So we can do it still using the VGOM. Now this time, the family is S ratio. What is S ratio? That's the sequential ratio. Okay, so the parallel is true. That means we assume the proportional odds assumptions. And that's the results. And the interpretation is here, and it's self-explained. You can take a look after class. Okay. Any questions? Before we end, I just want to remind you, I posted the old exam 2 and also the exam 2 announcement in the Moodles. Okay, I will post the solution for the old exams later. So you don't need to work on the old exams yet. You do it only after you prepare. Okay, so we finished the chapter 6. So the exam 2 covers chapter 4, 5, and 6. So you can start to prepare for the exam 2. Okay, so which will have the similar type of questions as the exam 1. Okay, that will be in person and in the reading halls. Yeah, reminds me. So reminds me, that's the best way. Sometimes I forget. Okay, so before the exam 2s, some of you just send me the email. Okay, just remind me. Any other questions? Okay, let's stop here.